Here we are going to build an AC to DC converter. If you stay with me to the end of this video, you will learn how to simulate in Proteus software. You will learn how to convert large AC, say 220 volts, to low DC, say 5 volts. You will also learn the relationship between RMS and peak voltage, the transformer settings with respect to the tones ratio, how to build a full wave bridge rectifier using diode instead of an off-the-shelf rectifier IC. You will also learn the filtering and smoothening effect of the capacitor, how to use a voltage regulator IC, and finally, how to read waveforms in an oscilloscope. So stay with me to the end of this video for all of this. We want to convert an alternating current into a direct current. The circuit that is responsible for that is called a rectifier circuit. So the first thing we will need here is an input voltage source. So I'm going to my generator. I'm picking a sine generator. And then I will also need a transformer. We all know the work of the transformer. To step down an input voltage to a lower output voltage, or to do the reverse, that is to step up a small input voltage into a larger output voltage. So let me search for a transformer. I'll be using this ideal transformer. Here is it. So let me place it here, and then let me connect this voltage source to the primary side of the transformer, and then this will go to the ground. Okay, I prefer to have this. Let me get the ground first. Then I'll place it here. All right. So I'm going to supply this voltage source with a value. So I'm double clicking. Then I want to give an amplitude. No, I want to supply my voltage source in RMS value, which is 220 volts. So I want to emulate one of the most popular value in AC transmission, which is the 220 volts. And then I'm setting the frequency at 50 Hz. Most transmission companies transmit their AC or alternating current at 50 Hz. So that's it. Then I'm going to change the values of this transformer like this. The only value to set here is the tones ratio, which is the ratio of the primary coil with respect to the secondary coil. Now, to know what this value would be is to have an idea of how much output voltage you would want from your transformer, that is at the secondary part or the secondary side of the transformer. So I'm supplying 220 voltage here, and I'm expecting to have 12 volts. I want 12 volts. So in order to get this tones ratio, all you need to do is to divide the input voltage by the expected output voltage. You will get a dimensionless value or number that you will impute here. It will be your tones ratio. Let me use this calculator to do that. Okay, I have 220 volts and I'm expecting 12 volts. So I'll divide it by 12 volts. This is the value I have as my tones ratio, which is 18.333. So I'm copying that. Then I'll paste it here. And then that's it. Now I'm done with setting the transformer. Now let me just be sure that I'm actually getting 12 volts here. So I'm going to use an instrument to measure that. So what's that instrument we will use? Of course, since we're having an input of 220 volts and it is an AC voltage, so we will be using an AC voltmeter to measure the amount of voltage here at the primary site. So here we are still measuring AC. Okay, so right now I'm going to simulate this. I'm expecting to get 220 volts here and 12 volts here if all our calculations are correct. So this is it, 220 volts, and then here we have 12 volts. Now I'm moving on to the next part of this circuit design. Now, what is responsible for the conversion of AC to DC? Probably the most central part of this design is the bridge rectifier circuit. Now, this rectifier circuit is a combination of 4 diodes. Now, Proteus would allow you to pick a rectifier. It has an off-the-shelf rectifier like this. Let me get that bridge rectifier. Bridge rectifier. I have it here. Now I can, okay, I didn't stop the simulation, so let me just stop that. So I have this rectifier. I can use it here. I can place that in this circuit, but I prefer to build mine with 4 discrete components. That's the diode. So let me get a basic diode. Okay, I have this. This is the generic diode. So I want to place this here like this. This is the simplest way to build this. Let them all face the same direction. And then I'll have this like this, this, like this. This will connect to this, and this will connect to this. Now we're going to have this here. And this will connect to this here. And this will go to the part that will be forming the DC ground. And then this will be forming the DC positive. All right. So I'm expecting to have some sort of pulsating DC voltage here. It's not going to give you pure DC, but this rectifier circuit here will ensure that the AC signal getting into this is being ripped off its negative components. So only the positive components will be left there. So it is not a complete DC. We would rather call it a pulsating DC because it's having some pulses. So I'm going to attempt to measure the voltage that is here by putting a DC voltmeter. So let me try that and see what I will get. I'm using an instrument, so I'm clicking on the instrument tab, and then I want to attempt to measure DC. So let me do that. Let me try that right here. All right. So let me simulate that to see. Okay. it's reading 0 because it's still having pulses, and DC is expected to be constant voltage flowing. So a DC voltmeter will expect to just read pure DC, but this is not possible because we still have to do some filtering here, and then this is where a capacitor will come into play. So I'll be placing a capacitor here. So let me search for a capacitor. So I have, let me pick this primitive capacitor. So I'll put that here. All right, so let me simulate this. So you can see we're having up to 16 volts DC. Now why is it 16 volts? I mean, from here is 12 volts, and we only expected that this bridge rectifier here would only do some rectification and still retain the value of this electric signal here, but this has been increased to 16. Why is that so? So I can even alter the value of my capacitor. So let me use 470 UF. These are standard capacitor values that you would get in the market. So this is reading 15.8. All right, let me just use that. So this could be a mystery, some kind of mystery, right? Because I'm expecting that here should be giving me 12 volts, isn't it? All right, I would explain to you why we are receiving 16 volts here. The input voltage to a transformer is AC. We already know that, and we've done that. And is expressed in RMS. We have, okay, let me stop that. We have RMS value here. We've picked the RMS option, which has a peak of 1.414 times as high as the RMS value. So it's a peak value. So if I click the peak value, this is what you would get. So if you multiply 220 volt by 1.4 volts, you would be receiving this value here as the peak value, which Proteus represents that as amplitude, which is 1.414 times as high as the RMS value, as is the secondary voltage also in RMS value. This bridge rectifier voltage here that we call the pulsating voltage is filtered and captured by this capacitor, which also stores it. It achieves the peak voltage of 1.414 times the AC RMS, which is 12 volts here, which is presented at the secondary here. Let me simulate this so that you can see. The pulsating voltage here that is supposed to be going as our output here has been captured by this capacitor. And this capacitor does that by just paying attention and making emphasis on only the peak value of this value here. And how do you get the peak value? There's a formula for that. It's the RMS times root 2, which is RMS times 1.414. When you do that, you're going to get a value higher than the RMS. So let me do that. If I multiply 12 volt by root 2, what do I have? Let me bring up the calculator. So let me do root 2 multiply by 12. Okay, here is it. We have 16.9. All right, we have 16.9. But here we are reading 15.9. So this is it. This is what happens. This is a full wave bridge rectifier, and by courtesy of this network of diodes, you will be losing about 1.4 voltage. Because it is a full wave bridge rectifier, for a half wave bridge rectifier, you will be losing 0.7 volts. But because it's full wave, you will be losing 1.414 volts. So from this value, I'm going to subtract 1.414 volts. So let me do that. I'm having 15.15, which is about 15.6 volts. So here we're having 15.9 volts, almost the same value. So this 15.9 volt is by virtue of the value of our capacitor. So you can always change this value to acquire the required output voltage here. But just bear it in mind that this voltage will always be higher than the AC voltage at the secondary part of this transformer because of the RMS to peak value relationship. So that being said, here you have a rectified voltage and also a pure DC voltage. To further have a purer voltage, you can use an off-the-shelf voltage regulator. So here I will be using an off-the-shelf voltage regulator, and I want to receive a 5 volt at the end of this circuit. I want to receive a 5 volt. So here we have about, is it 15.8 or thereabout, but we want 5 volts, maybe to power a microcontroller or something. So you can go to Peak and search for regulator. Okay, let me, instead of searching for a regulator, the name of the regulator is 7805. So 7805. So this is it, directly 7805. 7805 means it's going to give me 5 volts. So if I need 12 volts, I'll go to 7812. If I need 9 volts, I'll go to for 7809. So this 7805, it is an IC, a voltage regulator. It also does some filtering. It helps smoothing the voltage coming out from here. It does that in order to give you a more smoother output. We will be able to visualize that graphically by using an oscillator. So we will do that in a second. It is coming here and then here. Here we're expecting to have 5 volts. So let's see that. I'll be using a DC voltmeter as expected to read the voltage drop here. I'm expecting it to be 5 volts. So let me simulate that right now. Okay, so this is 5.01 volts. So it is time now to visualize the waveform at different stage of this entire circuit. So I'll be using an instrument called an oscillator. So let me place the oscillator here. Okay, this oscillator has 4 channels. It means we can visualize the waveform of 4 different signals at the same time. So I want to read the signal at this point here coming into this primary part or the primary side of this transformer, and then I will want this probe here should read the signal at the secondary part of the transformer, that is after the step down process has occurred. And then I want to also read the signal here after this purification or smoothing here, and then I want to read the signal after passing through a regulator here. Now all of these signals will be represented by these different colors, and they are called channels. Channel A is represented by color yellow, channel B blue color, channel C red color, then green for channel D. So let me simulate that and see. Okay, so this is it. You can see the waveform here. This is one for yellow, the other one for blue, then the pink, and then we have the green. Now I'm using the mouse. So when I roll the mouse roller, it zooms out for me horizontally so that I can see more of the oscillation going on here. Then if I want to zoom out vertically so that I can see the peaks of this waveform, all I need to do is to come here at this knob here. Let me set this to 0 first. Let's set this to 0. When I set this to 0, it means it will be giving you a symmetric representation where all the waveform will be represented within the screen so that you can see everything. So I'm putting the position at 0. Okay, so the blue is coming from here. That is the step down AC voltage. Now what I want is to place it still in the center at the 0 point. So where's the blue channel here? At the 0 point here. I like to see it at the 0 point. Let them all make their oscillation with respect to the same reference point. Okay, so for the voltage after the rectifier here, which is the red color, here is it. I want to also take it to a 0 reference point. This is it, the red one. So just notice how it's going up. Look at it here, how it's going up to the center here. And then that's the final voltage coming out from the regulator here. Look at it, represented in green. I want to also put it at the 0 point. Okay, so here we go. Now if you notice, now you can roll your wheel, the wheel of your mouse, to zoom in and out so that you can see the waveform. Now you could notice this, every box is a certain value and you can change this value here. Here we are saying that for every box is 38 volts. There's something very important I want you to see. This voltage here, for the AC voltage, the oscilloscope is reading this as the peak value. Remember, what we entered here was the RMS option. We ticked on the RMS option. But the oscilloscope will be giving us our reading in the peak value, which is represented as amplitude here, which is 311 or so. So let me simulate that again and then confirm that it is our peak value. So I'll select cursor. Once I select cursor and I bring this at the top, can you see it's reading about 311? Can you see that? That's the peak value. It's giving us the peak value. Now let me set this to 31.1. Let me see, can I do that? 31.1, 31.1. Okay, let me leave it like that, 31.1. It means if I multiply 31.1 times 10, I should be getting 311 or so. So that means from this center point to this peak, it should give me 10 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. So can you see how these grids are in order of magnitude of your voltage? So notice that this is the input voltage going into our transformer. Then this blue is the stepped down voltage. Can you see the magnitude is not that much? Still maintaining the same sinusoidal thing going on right here. But then we have the pink and the green. Now these are our DC voltage, almost appearing very straight. So this is how to use the oscilloscope to check your waveforms at different stages of this AC to DC conversion process in this circuit. So thank you for watching, and I hope that you've learned something here. Goodbye.